these photons interferes with Alice's incoming photon, a Bell state measurement is performed, and this Bell state measurement heralds the arrival of the second photon of the entangled pair to Bob. And this heralding enables this action of switching off detectors whenever you don't need them, so that the dark counts are rejected by an increased amount and the signal to noise increases. So of course you can now also think about cascading these relays to have an even more pronounced effect. But what needs to be stressed is that in these relays there is no amplification of quantum information whatsoever. So the qubits still get lost, but because you get better in doing, you get a better signal to noise ratio, you can actually get higher secure bit rates for longer distances. And for our implementation of the quantum relay, the core of this is a single entangled photon pair source, which I'll talk about now. So for such a source, there's a number of requirements that need to be fulfilled for it to work efficiently. And the first of which is we need to look at what the optimal wavelength is to enable long distance transmission of quantum signals. And for this, I've plotted here the optical loss in standard glass fiber. And you can see that in the third telecom window, around 1.55 microns, really that loss is minimal compared to any of the visible wavelengths or the first window around 900 or 1310 nanometers. And to show you just how pronounced that effect is, I've plotted here the transmission as a function of distance for 3 different wavelengths, so 900, 1310, and 1550. And you can see that you need to go less than 20 kilometers to have a factor 1000 transmission gain at 1550 over 900. So this is really quite striking, and it's a strong motivation for us to develop single photon sources in that window. Now, if you want to do a quantum relay, there are some properties that we need of our single and entangled photon pair source. And the first one of which is that we need a high entanglement fidelity, where we want on-demand entangled photons, ideally a compact and robust source, which can be tuned to our input qubits of weak coherent states. Now, in addition to the high entanglement fidelity, we also need to make sure that we can efficiently do the Bell state measurement, which is based on photon interference, and that requires that we need coherent photons to do this Bell state measurement, and also sub-Poissonian statistics for efficiency of our protocols. So this is a little bit our wish list, what we would like to have from our C-band quantum dot source, and this is what I'll be talking about in the coming chapters. Just to quickly show you what options we have to develop C-band photon sources. Actually, you all know probably that a lot of single photon sources have been developed for the visible and near infrared range of the spectrum. So this includes quantum dot in various systems. This includes defects in diamond, which have enabled lots of cool things, and also a whole host of new 2D materials and different things we can think of. And there's been some research at 1310 where there's been tunable quantum dot diodes reported, or also recently there's been progress having defects in silicon which can emit at this wavelength. But at 1550 C-band, there's really not been all that much going on so far. So there is quantum dot technology, and there are really only scattered reports of defects, for example, in silicon carbide or gallium nitride. So what people often resort to is wavelength conversion instead. But today I'd like to show you that indium phosphide biased quantum dots are really promising for C-band applications. So now I'll actually start speaking about quantum dots with a brief introduction to our C-band quantum dots. So the working principle is that we have a semiconductor structure like this, where we have a Bragg mirror at the bottom. We have an intrinsic indium phosphide region, indium arsenide quantum dots, and these are overgrown with another Bragg mirror just to help direct emission towards the top. And our dots are grown by standard semiconductor technology, so MOVP in our case. And the reason why these quantum dots emit in the C-band rather than the more standard wavelength range around 900 nanometers, you can see in this graph here. And it's basically because the materials we have, so indium arsenide here and indium phosphide, they are closer in lattice constant than the more standard indium arsenide and gallium arsenide. And that leads to a reduction in strain in these structures, which pushes the emission out to the telecom C-band. Here is a graphic of our device and how it is grown. So As I said, we have a Bragg mirror. We use droplet epitaxy for our dots. So this means that we deposit indium droplets on our indium phosphide surface. These droplets are then crystallized in an arsenic atmosphere to form indium arsenide quantum dots. They're overgrown with a p-dope top mirror. We can then etch mesas and gauge this to apply voltage if we want, and also use electrical injection for our diodes. And this is a picture of the final device where you can see these are the top gates, this is the mesa, and this is the bottom gate. If you apply a voltage to one of these devices, you get an image such as this one shown here. But you can see that each individual little dot here is one quantum dot. And the shadow that you see here is the top gate of our device. Now, if we focus with our confocal microscope on one of these spots, you can see these sharp lines that correspond to different charge combinations in our quantum dot. So you can identify the exciton and the biaxon, for example, and filter out that light. And we can see that this is really a true single photon source by doing a Hanbury, Brown, and Frisch measurement, where the probability of finding two photons emitted at the same time is just 11%. If we want to optically excite the dot, that's possible too. So we use this a lot because it's possible to operate the diode at lower temperatures by using photoexcitation rather than electrical excitation. And in this case, we use above band excitation at 780 nanometers. We get the same sharp lines, similar T2. So we can really use either of the two methods, whatever we want. And we get low density that is easily, so it's easy for us to address single dots with confocal microscopy. So now that we know how these dots function, how we create our devices, let's have a quick look at the coherence and entanglement properties of the photons. So first, I'll show you how coherent our photons are, and then how we measure the entanglement. So this is how we measure coherence time. So we have a fiber-based Michelson interferometer where the photons from our qubits, they impinge on a beam splitter. There are two fiber-based arms. One of them has a fiber stretcher, which is able to just introduce a little bit of a delay between the two arms to record interference fringes. And then the other one has a delay line, which is able to just do a more coarse adjustment of that delay. Then the two arms are recombined and we measure the output on a spectrometer. We look at the contrast of the interference fringes as a function of delay. This is what we find for an exciton. So you can see two effects here. You can see that overall visibility decreases, as you would expect, and that envelope actually gives us the coherence time of our photons. But you also see a beating pattern, and this beating pattern is due to the fine structure splitting of the exciton, which I will also explain later. And yes, and so the last thing you can see is that for low excitation powers, we get longer coherence time than for higher excitation powers. So this is 3% of the saturation power, and this is 75% of the saturation power. Now, we can do these measurements for a whole range of powers to get a power dependence like this, where we see that at very low powers, we get coherence times up to 1 nanosecond, which is really quite nice and a record for C-band devices. And then this coherence time decreases for higher excitation powers. But of course, what increases instead is the count rate of the dot. So in the end, for any application, we want to be somewhere in the middle where we get an appreciable amount of photons out, but still also a nice coherence time to resolve our measurement. To put this into perspective, the lifetime of our dots is 1.65 nanoseconds. So from this, we can calculate how close to the Fourier limit we are, and the value is about 0.3, which is actually a pretty good value, given that we're exciting the dots non-resonantly, and certainly in the C-band, I don't think anyone has seen anything better than that. So the next thing we do is we interfere our coherent photons with a telecom laser, and this is to simulate what would happen in the quantum relay, where we also have the input qubits provided by a laser. So here the effect is that if two identical photons impinge on this beam splitter, they will always leave this beam splitter through the same port. And in our case, we use then a second beam splitter to measure increased coincidences in one of these arms. So these correlations will show up as a bunching effect. Two photons arrive at the same time, in addition to the normal properties of our quantum dot. And in fact, if you look here, this is a correlation measurement between these two detectors. And if we have co-polarized identical photons, this is exactly what you see. So you see a bunching at zero delay. versus for cross-polarized photons, we just get the profile of a single photon source on a background provided by the laser photons. This is exactly what we would expect. From this, we can now calculate the visibility, which depends on the count rate ratio between the laser and the single photon source. And this is basically just a measure of how much of the laser is really the single photon Fock state that can interfere with our quantum dot photons, and how much are all the multiple number Fock states. And so if we just simply calculate the visibility from these two graphs with this formula, we can see that the maximum visibility, if we use favorable settings, so low powers and a high ratio of quantum dot photons to laser photons, we get about 72% interference visibility. If we use more realistic scenarios, so powers as well as ratios, we get about 60%. So as I was saying, a limiting factor is this ratio. So if we plot what we would expect, the visibility we would expect as a function of the ratio between quantum dot photons and laser intensity, we should be in a perfect scenario where the G2 of the dot is really 0. We would follow this curve. If we have finite G2, then we would be on these curves. And in fact, this is exactly where we are for our measurements. So we know that the main limiting factor for our interference is that the quantum dot is not a perfect single photon source, but we have this G2 of zeros around 10 to 18%. But nevertheless, we are quite happy with these results. So now moving on to entangled photon pair generation. Here we use the bi-exciton photon cascade to generate the entangled photon pairs, where initially the quantum dot is occupied by 2 electron hole pairs, and these then recombined one after the other to leave the dot in the end empty. And this can happen in 2 ways, depending on which of these spin combinations recombines first. We get either an H photon out, followed by another H photon, or a V photon followed by another V photon. This is if we are in the actual eigenbasis of the quantum dot. And in this case, we get really the ideal Bell state out that is depicted here. Now, if the photons are emitted in a superposition basis, and because of the fine structure splitting of the dot, because these states are not completely identical in energy, the superposition will actually pick up a phase during the lifetime of the exciton, which is shown here. So instead of just a straightforward Bell state, we now get a time-dependent, time-evolving Bell state with a phase depending on this fine structure splitting. And we can think about this as these superpositions rotating along the equator of the Poincare sphere as a function of the exciton lifetime. To measure our entanglement, we just separate our exciton and bi-exciton photons using a grating because they are emitted at different wavelengths. And then we use 2 polarizing beam splitter setups with superconducting detectors. And this is just to check that if we have a certain polarization for the exciton, what is the polarization of the bi-exciton? And it turns out, as you can see here, that we're in the HV basis. Really, if we have an H-polarized exciton, it's very likely that we also have an H-polarized bi-exciton, and very unlikely to have cross-polarization. And this is exactly what we would expect. Whereas for the superposition basis, we have an oscillating correlation, and this is also what we would expect based on the fine structure splitting effects that I've shown you on the previous slide. Now, if we measure these correlations in 5 different bases, so HV, dA, LR, as well as diagonal bases, we can calculate the fidelity to a maximally entangled Bell state. And this is shown here as a function of time delay. So as a maximum, we get about 87 plus minus 5%, and our entanglement lasts for about 1 nanosecond before the correlations then decay below the classical limit. One nice additional feature of our dot is actually that we are able to measure correlations up to 96 Kelvin electrically injected before finally the correlations dip below the classical limit. So we can generate entangled photon pairs even at elevated temperatures. Okay, so next I'll show you how we'll put these ingredients together. So the good coherence times, good interference, visibility that we have, and the entanglement to actually run a quantum relay in the telecom C-band. And what happens here is that we have an input photon provided by Alice, which is just a polarization encoded photon, which she sends over to Charlie. At Charlie, we also have our entangled photon pair source. We use the exciton photon to interfere with the incoming qubit and do our Bell state measurement based on the two-photon interference. And this then heralds the arrival of the photon, the biaxial photon in this case, at Bob's station. And we can then compare the qubit that arrived at Bob, or the polarization of this qubit, with whatever Alice was sending in to check whether our teleportation has worked. So what we need for this is 3 photon coincidences. So we need these 2 detectors to click to know that we've successfully done the Bell state measurement. And then we can measure which polarization has arrived at Bob and check whether this was the actually intended polarization or not. This is a purely probabilistic measurement. And because with linear optics, you can maximally detect 2 Bell states out of 4, our efficiency is intrinsically limited to 50%. And in fact, in our particular implementation, we only measure 1 Bell state, so we're even limited to only 25%. So to determine the teleportation fidelity, we do post-selection. So we look at the time when each of these photons arrive. And there are 2 timescales that are important in this process. So here's a simplified sketch. We have the incoming laser photon, we have the quantum dot exciton photon, which interfere here for the Bell state measurement. And of course, this interference will only work for as long as this exciton photon is coherent. So the coherence time of the exciton photon will limit the visibility along this time axis, so along the axis that measures the time delay between these 2 photons, which we call tau Charlie. The second limitation that we have is that because of the fine structure splitting, there is a phase being picked up between the exciton and the bi-exciton. So if we look at correlations between the detector click here and the detector click here, eventually these 2 will be out of phase. And that means that the fidelity is lost as well. And this will happen on a time order that's the inverse of the fine structure splitting. So just go through this. This rotation will limit the time scale for how long we can measure teleportation at Bob. So in the end, our measurement looks like this. So what we see is along Charlie's axis, we project, we just see a peak where the width of this peak is given by the coherence time of our exciton photon. And along Bob's axis, we see an oscillating pattern where the quantum beat comes from the fine structure splitting of the quantum dot. So now we can zoom in on this particular peak here, and we can see that we can roughly estimate what sort of window size would be appropriate to determine our maximum fidelity. But obviously also, if we make the window size bigger, then the peak will be averaged out more, but more photons will contribute to it, so the noise will go down. Versus if we really zoom in only on the peak, then we'll have more noise but higher fidelity. And that's what I can show you here on this graph. So this shows you as a function of number of teleported photons, which means simply how big is this window, that how big we zoom in around that peak. That if we make the peak very small, we get very high fidelities, but worse statistics, so we get large error bars. Versus if we make the window bigger, fidelity drops, but the error bars also get smaller. So what we've taken in the end to measure how well our teleporter performs is the point of highest significance, where we are the most sigma above the classical limit. And on this particular point, we have a mean fidelity of 83.6%, and we are 7.8 sigma above the classical limit. And this just means that, so 83% of the time, the correctly polarized photon has arrived at Bob. And of course, we've done this now in 6 different bases, and in every single basis that we've measured, fidelity has been above the classical limit. And this just in. Okay, so that brings me to the last chapter of my talk. So I'm going to show you now how we can run a relay, but make it compatible with standard QKD systems. So for us, this means make it compatible with the gigahertz clocked source and also with time bin encoded qubits. So I'll show you in this chapter how we make the gigahertz clocked pulses, how we characterize the emission of our source using these gigahertz pulses, and finally how we do the time bin encoded quantum relay. So the idea of how we do this measurement is that we have the exact same relay station that we had before, but now to make it compatible with time bin encoded qubits, we have conversion units that take the time bin input and convert them to polarization. And the same for the outgoing photon. So we have a polarization encoded bi-exciton photon, which is converted to time bin before being sent on to Bob. So the measurement that we're going to do is we first simulate a gigahertz clocked time bin QKD input by using a laser, and then converting the polarization encoded qubit to a time bin qubit. And this is done with a unit like this, but it's really quite simple. So if we look at a random superposition between H and V of our polarization qubit, we split the H and V polarization components into two different arms using a polarizing beam splitter. In one of these arms, we introduce a delay so that what comes out on the other side, once we recombine them on another polarizing beam splitter, we have now a hyper-entangled state, which has an early H and late V polarized pulse. Of course, we can now reverse this at this station by just putting the delay in the other arm. That will make the two pulses overlap again. And then in the end, we measure that Bob has received the correct time bin once we've done our relay measurement with the gigahertz pulsed entangled photon source. So to run these gigahertz clocked pulses, we've come up with a flexible scheme to produce these laser pulses. This applies both for the input qubit, which is at 1550 nanometers, and for the quantum dot excitation, which is non-resonant at 1310 nanometers. And for both of them, we have a simple scheme where we have a CW laser, and we have an EOM, and followed by a polarizer. So then what we do is that using a pulse generator, we apply a pulsed pattern to the EOM, which then rotates the polarization of the laser in and out of that polarizer at the end. So basically, our laser polarization is just rotated by the EOM in and out of the allowed polarization that's being sent through. And this works actually very nicely. We can generate quite narrow pulses with a full width half max down to 147 picosecond. And that's just limited by the rise time of our pulse generator. And we can also make this at gigahertz repetition rates, where we get about 3 orders of magnitude compression between the peak and the noise. So now this is a quick slide to show you what happens to the entangled photon source once we drive it with these very fast pulses. The first thing we do is we do a lifetime measurement where we correlate the arrival of a quantum dot photon with the arrival of a laser photon. So if we do this at slow clock rates, you can see really the decay of the quantum dot exciton and bi-exciton population before the next pulse then hits them. But if we now increase the clock rate to 1 gigahertz, there is no time anymore for the exciton and the bi-exciton to relax before the next pulse hits them. And you can see that now basically all we get is like a little wiggle for the exciton and the partial emptying of the bi-exciton states before the next pulse will hit them. So the question is, how does this affect the performance of our source as a single photon source? So for this, we take the quantum dot photons and a beam splitter, and we correlate now the arrival time of these two photons. So at 100 megahertz again, what we see is we have these well-separated peaks with a little re-excitation feature, but basically the center peak is completely absent. If we drive at 1 gigahertz, basically this looks like a CW measurement now, because these little wiggles have been averaged out in the correlation. But what is kind of nice to see is that at 0 delay, we still get a T2 of about 9%, which is the same as if we drive it slowly. So we did one last measurement to show that within one pulse, actually, we still only get 1 photon. And that measurement is to do this T2 measurement in a separate way. So here we correlate the arrival of the two quantum dot photons with the arrival of a laser photon. And this leads to a 2D map like this, where the two time delays are just the delay between the laser photon and either of these two. And what you can see here is that when the delay is equal between these two photons, we really see no photons arriving at the same time for the entire duration of this pulse. So we get this diagonal where basically there's the absence of coincidences, the absence for the entire duration of the pulse. And that is quite nice to see. So it means that even at gigahertz clock rates, each single photon pulse only carries 1 photon at most. So this is the slide that shows you how the entanglement will change or not if we start driving the diode faster and faster. So for this year, we've done a 2-photon density matrix at 0 delay in a 96 picosecond window, where we've just measured a complete set of correlations in unbiased basis, and we found that the entanglement fidelity is 88%, concurrence is 0.8. And if we do this at non-zero time delay, we can still recover the oscillations which are due to the fine structure splitting as we had before. Now, I've done this measurement for a range of frequencies, so at CW, 100 megahertz, and then also 1 gigahertz, using the method I've shown you previously, and also this density matrix method. And what we can say is that the entanglement fidelity actually does not decrease if we start driving the quantum dot faster and faster. So this all bodes well for our final measurement, which is teleporting the time bin encoded qubits. So here, a slight modification to the previous sketch. What we do is we first prepare input qubits in a superposition of early and late bins, which here are separated by 5 nanoseconds. They go through the conversion unit. We then perform the Bell state measurement in the polarization basis and check the polarization of Bob's photon. So this is a sketch of our time bin encoded qubits, which can be either in a superposition or also just in the early or late bin. So this is a 3-photon coincidence map, just showing you the coincidences we measure at the relay station in a superposition basis. And what you should pay attention to here is the 0 delay. So this is here and here, where you can see that in the expected polarization, we do see photons, and in unexpected polarization, we don't. And we can calculate the fidelity of this. We zoom in around 0 delay, and also repeat this measurement in the other bases. And we get a mean teleportation fidelity of 82%, which is in our case 10 sigma above the classical limit, which if we use a post-selection window of about 228 picoseconds. So this is all done with post-selection still. But the nice thing to say is this conversion unit that we have does not really affect our teleportation fidelity. Now, the final experiment that I will talk about is also converting Bob's output photons back to time bin. So we prepare the time bin input, we perform the Bell state measurement polarization basis, just like we've done before, and then we check the time bin of the arriving photon at the end. So what happens here is now we see this pulse behavior in our 3-photon coincidence measurement. And this is the plot we get when we send in an early laser photon and we get a late biaxial photon out, which is what we would expect due to how our teleporter works. And I'll draw your eye here to what happens at 0 delay. So if we send in an early laser pulse, we get a pulse out at 0 delay. If we send in a late laser pulse, then instead of getting the pulse at 0, we get it at -5 nanoseconds delay at Bob, so that means the teleporter has converted an early laser photon to a late biaxial photon and a late laser photon to an early biaxial photon. And to show this more clearly, taking a cut of this data, these two data sets along the Charlie 0 axis, this is what is shown here. Here you can see that if we send in an early laser photon, then we get out a late biaxial photon, which arrives 5 nanoseconds after the photon we would get out if we send in a late polarized laser photon. Now we can calculate again the fidelity of this teleportation process just by counting the number of photons that have arrived in the correct time bin versus the incorrect time bin, and we get a post-selected teleportation fidelity of about 89%, which is still the same ballpark number that we've had before. So this already brings me to my conclusions. I hope I've shown you that with single and entangled photons, we can really construct devices that are useful for the development of future quantum networks, such as quantum relays and teleportation. These can provide intrinsic security at network nodes and applications. They can enable longer communication distances and also higher efficiency in principle. And our indium phosphide, indium arsenide telecom quantum dots are really a promising technology for a range of these applications. And the highlights of the talks were that we have an electrically operated device that we want for the simple generation of single and entangled photons. We can teleport polarization encoded qubits generated by a laser source. And we can also do a quantum relay, which is compatible with time-binding coded qubits, which are used in quantum key distribution experiments. So with this, I'd like to thank you very much for your attention, and also thank all the people who were involved in these experiments, in particular my student Matt Anderson, and the whole host of people at Cambridge Research Laboratories, people at University of Cambridge, and also at Sheffield, who have actually grown our quantum dot samples. And these are all the funding agencies that made this work possible. Thank you very much.